This is Mr. Merrill. We're going to look at this elevator problem. So let's say you step into an elevator and stand on top of a scale, and I tell you that that elevator and you inside it are at rest. Well, being at rest is a special case of having a constant velocity. It's having a constant velocity of 0. So the most important thing that tells you in terms of this problem is that you have an acceleration of 0. If you have an acceleration of 0, you can infer that there are no net forces, because net forces would cause an acceleration. And if you know that there's no net forces, then you know all the forces added up must be 0. The only two forces that you should consider are the normal force from the scale and your weight, the force of gravity pointed down. So we're looking at a scenario where the scale reading is the same in magnitude as your force of gravity, and this is what you're used to. You're used to standing on a scale and having that be the idea of your weight, but in reality it's measuring the normal force, and you're kind of assuming that you have 0 acceleration, which is a pretty decent assumption. So let's look at a scenario where you're standing on the scale but you don't have 0 acceleration. How does that affect things? So here I am standing on a scale and I have some acceleration in the positive direction. Well, for me to have some acceleration in the positive y direction, I have to have some net force in that positive y direction. For me to have some net force in that positive y direction, I must have a normal force that is greater in magnitude than the force of gravity. So this means that the scale is pushing on me harder than my own weight to accelerate me upwards, and that also means that the scale is going to read a larger number than what my weight is in actuality. So let's go ahead and solve for the acceleration. We can kind of set this problem up how we would do any other problem. So we have a force diagram here, and we're going to write the forces in component form. So there's no x component. All the magnitude is in the positive y direction for Fn. There's no x component for gravity either, and its entire magnitude is in the negative y direction. And we can go ahead and substitute that for mg, which we're used to doing for gravity. Okay, so now we can use Newton's law. The sum of the forces here are not going to equal 0, but we do know that the sum of the forces in that y direction have to equal the mass times the acceleration in that y direction. Right? This is Newton's second law. It's saying if you do have a net force, which we know we will, then that net force must equal the mass of the system times the acceleration of the system. So we can go ahead and substitute in what that sum is, so that'll be Fn minus mg. And we can solve for this acceleration. And it's just a matter of plugging in any known values to find that acceleration. One thing that gives some students trouble is they'll look at this and they'll say, I don't have the mass anywhere in the problem. Well, you might not directly tell you the mass, but remember, if it tells you the weight, it's always easy to find the mass from that. So for example, in this problem, let's just say that this weight is 500 newtons. Then you could just rearrange this relationship between mass and weight. Plug in whatever the weight is, divide by the strength of gravity, 9.8 newtons per kilogram. And this is just an example. Say your weight is 500 newtons. Then you can calculate the mass. And here I think that would work out to be 51.02 kilograms. And then you could use that somewhere else in the problem. So don't worry if you don't have the mass directly. If it gives you the weight, it's always easy to find. So this is a general idea of how to calculate something like the acceleration. And the other thing that confuses people are, what are the options once you know that the acceleration is, say, in the positive y direction or in the negative y direction? Well, there's one obvious case for when you have a positive acceleration. That is, the object is accelerating in the direction of motion. So that just means that the object is speeding up while traveling up, and we can imagine that as a force diagram. It would look something like this. So those are velocity vectors getting bigger. Those velocity vectors are getting bigger because there's some constant acceleration in the direction of motion. But the other scenario that's harder for people to think of is when the acceleration is pointed in the opposite direction of motion. So here we can imagine traveling downwards in the negative y direction. So we have velocity vectors traveling in the negative y direction, but they're getting smaller, and that can be explained by the fact that there's some acceleration still in the positive y direction. So both of these scenarios have a constant acceleration in the positive y direction. And from just knowing the scale reading and knowing the forces on the system from that, we can't tell which situation is happening, right? Both are equally possible if this is the only information we have. So hopefully that helps a little. If you have any questions, just go ahead and shoot me an email.